In this video, I will introduce the mass moment of inertia. So what does the word inertia mean? The answer is, inertia is the resistance of any physical object to any change in its motion, including a change in direction. In other words, it is the tendency of objects to keep moving in a straight line at constant linear velocity, or to keep still. We know that forces cause translational motion, while moment causes rotational motion. According to the Newton's second law, the forces equals to mass times acceleration a. Or it could be written this way, that the acceleration a equals to the force divided by the mass m. As you can see here, mass is the resistance to translational motion, and that's why sometimes mass is also called the inertial mass. Since moment causes rotational motion, so can we write something similar that relates the moment to the rotational motion of the object? Indeed we can. Same to the Newton's second law, the moment equals to Im times angular acceleration alpha. As you can see, moment and angular acceleration alpha are both vector and they have the same direction. And we can rewrite this equation into this form, alpha equals to m over Im. If you compare it to the equation above, you can find that this item Im is a resistance to rotational motion and is known as mass moment of inertia. And the subscript m stands for the mass moment in order to distinguish from the other moment such as air moment or rotational moment. So how is it defined? Just like the moment caused by a force, the moment of inertia is always calculated about an axis, say axis AA, on a rigid body. For a differential atom with a mass of dm, we can find the perpendicular distance from it to the axis, r, and the mass moment of inertia about this particular axis AA is the integration of r squared times dm, integrated throughout the entire body. So unlike mass, which is absolute, mass moment of inertia is relative, and is different when calculated about different axes. So it is clear that in the moment equation, the two items have to be calculated about the same axis. Now let's take a look at the example. Here is a rod rotating about its center of mass O. So apply our equation, we can get IO equals to the sum of MI times RI squared. And since M equals to rho times V and V equals to A times L, M finally is rho times A times L. Then we can do the integration about this equation, and finally we got, for this bar, about the center of mass inertia is mass times length squared over 12. Now if we move the axis to a new point O, the new equation became IO equals to IG plus MD squared, which is also called the parallel theory. And solve this equation, we can get the IO equals to mass times length squared over 3. Then we can take a look at the example from the lecture notes. So the pendulum is suspended from point O and consists of two thin rods, each having a mass of 5 kg. Determine the pendulum's mass moment of inertia about an axis passing through the pin at O. To solve this question, we have to separate this rod into two parts. One is OA, the other one is BC. For the moment of inertia of rod OA about an axis perpendicular to the page and passing through the end point O as a rod, we have IO equals to 1/3 times mass times length squared. So we got 1.667 kg meter squared. And for BC, we can apply the parallel theory. Then we can obtain the IBC equals to 5.417 kg m squared. And finally, for the mass moment of inertia of the pendulum about O, we sum two parts together. We have 7.08 kg m squared. That's the final answer.